Hi, my name is Igor Shalyminov. I'm a PhD student at Heriot-Watt University. In this talk, I'm going to present a hybrid generative retrieval transformer-based approach to dialogue domain adaptation, part of Dialogue System Technology Challenge 8. The work was done during an internship at Microsoft Research Montreal. So let's start by looking at the overall state of neural dialogue modeling and what data is used for it. So we have generative models like sequence-to-sequence trained on Reddit dataset containing billions of comments, or Open Subtitles dataset containing hundreds of millions of lines. We have transformer-based models like GPT-2 used by Hugging Face. It featured a multi-stage training procedure with a base training stage on a web text corpus containing millions of documents, and with a fine-tuning stage, featuring datasets like Persona Chat for chat-oriented dialogue or Multivos for goal-oriented dialogue, both containing tens of thousands of dialogues. We also have retrieval models normally used in production systems, like Replica's context response similarity model trained on Twitter Stream containing tens of millions of tweet response pairs, and a deep semantic similarity model-based ranker in Microsoft's Xiao ICE system trained on a private dataset of tens of thousands of labeled dialogues. So let's see how these models trained on big datasets work in practice. For example, we're developing a dialogue-based product, and we need to scale it to a new domain, or we need to add flexibility to our product, or we just need to maintain the overall fast development cycle. And the datasets we train our model on make it too static and too inflexible, and probably the one step missing in this diagram is to adapt our model to small and focused in-domain dataset. And this is the problem we'll be tackling in this talk. And here's how this problem is formulated in the STC-8 domain adaptation framework. So we have this model, and we have a dataset containing multiple domains, each one containing multiple tasks. And for example, a movie domain may contain tasks like book a movie ticket, cancel a movie ticket, recommend a movie, and we're training our model and seeing how it generalizes to other domains in the dataset. And this is our base training stage. In the adaptation stage, our model will become the base model, and at each given time, we'll be getting batches of support dialogues coming from a specific domain, like here the domain is probably flight booking. And we can adapt our model to these dialogues by, for example, running additional training epochs on them, or by holding them out for further retrieval, or by completely ignoring them. Eventually, we'll end up with the fine-tuned model, and we'll get a target context from the same domain as support dialogues to predict our response using generation or retrieval or any other logic. And here's our model, Generative Retrieval Transformers, or in short, GREATR. Let's take it step by step. At the base training stage, we use the normal GPT-2 training procedure. We represent our dialogue as three independent sequences: a sequence of context tokens, a sequence of speaker IDs, and a sequence of turn IDs. We encode them independently using the transformer encoder and average out the embeddings into the final representation. We train our model using the multitask objective, with the first task being response generation in a language modeling way, using the transformer-based decoder, and the second task being the next sentence prediction, using a separate head for that. For this task, we pass two inputs into our model. The first one is the target dialogue context plus the goal response, and the second one is the target dialogue context and a distractor response from the dataset. And the task of the next sentence prediction head is to predict something close to 1 in the first case and something close to 0 in the second case. And this is exactly the Hugging Face setup for Conv challenge. For the adaptation and prediction stage, we do the following. We fine-tune the model to the support set in the same fashion. Then we generate the response using the language modeling head. Then we look at the support dialogues and encode every support dialogue context using the same shared GPT-2 encoder. And we find the closest one to our target dialogue context in the KNN fashion. Then we pick the next turn in that dialogue as our retrieved candidate. We then pass the two response candidate to our model once again, by re-encoding the target dialog context plus generated tokens and the target dialog context plus retrieved tokens, and run the next sentence prediction head on them. Whichever gets the highest next sentence prediction score becomes our final answer. So let's look at our data sets. In our DSCC8 task, we are given the MetalWAS dataset containing 47 domains, more than 200 tasks, and 37,000 total dialogues. And we have a pre-processed version of MultiWAS containing 7 domains and a bit less than 3,000 dialogues. How do we use these datasets? So for training, we only use the train split of MetalWAS. And for evaluation, we use the held out part of MetalWAS and the whole of MultiWAS. And we run the following evaluation stages on those. The main evaluation stage is human evaluation on MetalWAS, where human judges on mTurk were asked to assess the systems against 4 criteria: appropriateness, informativeness, usefulness, and easiness to answer. For that, the systems were paired using the multisort algorithm, and the judge's task was to select the best of each pair. On the graph, we see the 5 contestant systems, as well as the gold reference response from the dataset in blue. We can see that our system in orange consistently outperforms all other systems and stands right below the reference point in the overall rankings. The interesting bits here are that in appropriateness, our system is almost tied for the first place, and in usefulness, it's almost tied with the rank below. Why that happened might become clear later on. Our second evaluation stage is automatic evaluation on MetalWAS. We have 2 setups here: MetalWAS pure task, where the support dialogues and the target dialogue come from the same domain and the same task, and MetalWAS cross task, where the support dialogues come from the same domain but an arbitrary task within it. Here we measure the overall language generation quality in terms of blue and rouge scores. We have the following baseline: 2 retrieval baselines provided by the organizers and differing in the way they encode dialogue. The first one using BERT encoder and the second one using sentence piece plus fast text trained on rated dialogues. These are visualized in blue. We have another baseline, an HRED-based model, in green, and we have the 3 versions of our model. The vanilla GPT-2 not using the support data at all, GPT-2 fine-tuned to support data but not using the retrieval logic, and our most complete grader model, visualized in red. We see that the vanilla GPT-2 struggles to outperform the baselines most of the time. Fine-tuning to support data helps it a bit, and using the retrieval logic further improves the performance. It's especially visible in the pure task setup. In the cross-task setup, the improvement is not very significant, and in terms of rouge score, retrieval logic even degrades the performance a bit. But it will help at our last evaluation stage, automatic evaluation on MultiWAS. At this stage, assessed is the goal-oriented performance of the systems in terms of F1 scores over intents and slot types in the responses. The systems were exposed to MultiWAS data only at the adaptation stage. We have the same baselines here, as well as the other contestant systems in gray. We can see 2 interesting bits here. Firstly, the GPT-2 model fine-tuned to support data performs significantly worse than the vanilla one, even though the vanilla one knew nothing about the MultiWAS data at all. The reason behind that might be the fact that MultiWAS data is way less varied than MetalWAS, and it's much easier to overfit too. But anyway, the use of the retrieval logic compensates for that. Secondly, Team A's system outperforms our model significantly in both metrics. This is especially interesting given human evaluation round standings. So it might be the case that this system was trained mainly to strictly follow the reference response, rather than generating some natural and appropriate answers overall. So let's take a look at how our model decides whether to generate or retrieve responses. So on MetalWAS, we can see that the model decides to retrieve pretty frequently, but still, in the majority of cases, it generates responses, and retrieval logic is used rather as a fallback in case of the lack of confidence in the model's own generated responses. On MultiWAS, the situation is overall the same, but the trend is for more retrieval. It may be due to the fact that on this unseen data, the model is less confident in its own generated responses and chooses to fall back to retrieval logic more frequently. Finally, let's take a look at some example responses from our system. Here, the system side, gray bubbles, is done by a human wizard. The user side, the blue bubbles, is modeled by us. And the last blue bubble is the system's predicted response. And the green bubble is the gold response. Here we can see that our predicted responses make perfect sense in the dialog contexts and are perfectly relevant and natural here, but share little to no word overlap with the reference responses whatsoever. For example, in the first dialogue, the last system's question is "What do you want to know?" Our response is "Who was the founder of Rome?" And the gold response is "I like history, where should I go?" As you can see, both responses seem natural and relevant to this dialogue, but they share absolutely no words in common. In the second example, the system question is "I have two options available for you. Do you care about parking?" Our response is "No, I don't care about that, surprise me." And the gold response is "No, parking is not an issue. What do you think is the best option?" As you can see, both responses work here, but the only word they share in common is probably the word "no." That might explain why the responses produced by GPT-2, with the additional source of diversity being the top P sampling enabled in the decoder, are preferred by human judges, but at the same time, in the automatic evaluation on MultiVoice, weren't the best in strictly following the reference. So to recap, we have presented a hybrid generative retrieval model for dialogue domain adaptation. We saw that it's able to generate natural and diverse responses in a variety of domains, but still, we saw that conversational goal completion remains an open problem for transfer learning approaches. And in the future, we would like to explore ways to be even more data efficient in domain adaptation in terms of the amount of support data, for example, in the few-shot or zero-shot setups. We think that meta-learning could be an appropriate technique for that. And with that, thank you very much for your attention, and please check out our resources.